Hi, my name's Lloyd, and I'm here to talk to you about triangles. I don't have a computer science degree, but I did spend the last 3 years working as a graphics engineer on open source map rendering libraries at Mapbox. And now I work on tools for exploring and analyzing satellite and aerial imagery at a company called Descartes Labs. So everything the light touches is a triangle. Actually, the Lion King was hand-drawn, so no. But it did have some computer animation. The Wildebeest Stampede, notably, was computer animated, but it's not triangles. Toy Story was released a year later, and that was the first fully computer animated film. So you can say that everything the light touches in Toy Story is a triangle. Just so we're all on the same page, when I talk about computer graphics, I just mean images that are drawn or created, images or videos that are drawn or created by computers. And rendering is just the verb we use to describe the process of computers drawing. So, because I don't have a computer science background, I had to learn a lot on the job when I started working on map rendering. And one of the first things I learned was that everything that appears on the screen when the map shows up is at its most basic form, a triangle. In fact, with the exceptions of points and single pixel wide lines, triangles are the only thing that most modern graphics hardware can draw. Now, of course, when you play a video game, explore an interactive map, or watch a beautifully animated Pixar film, you don't see triangles. And that's because there has been a few decades of research by very smart people into different techniques for how to use triangles, math, and physics to render rich, dynamic, and even photorealistic scenes with computers. In fact, there are dozens of subspecialties in computer graphics that bridge the studies of mechanics, optics, light, color, design, art, computational geometry, electrical engineering, and more. So if any of those things are interesting to you, I highly recommend learning a little bit more about graphics. You might like it. Okay, so why do computers render mostly triangles? I didn't really know the answer to this question myself for a while after I started working as a graphics engineer professionally. And it turns out triangles became a standard in the graphics industry because of the need for drawing to be very fast and because of some convenient geometric properties triangles have that make drawing them a lot easier. I wish that I had done the quality of archival research that Eric Fisher did to actually figure out when triangles were decided upon, but I do not know. I did some light Googling, but that's it. Okay, so before we think about what makes triangles a good shape for computers to draw, it's helpful to understand what actually needs to happen for a computer to render an image. So the software on your computer needs to tell the display which color to paint each and every pixel it controls. Usually there's a special buffer of RAM. Sometimes it's on a graphics card like a GPU. Sometimes it's not. It's just in your regular memory, called a frame buffer. And that contains a full frame worth of pixel data and is used to drive the display, monitor, projector, whatever is being used to as the graphical output of your computer. A frame buffer is really just a memory buffer. You can think of it as an array that has red, green, and blue color values for each pixel in the display. Some frame buffers have alpha or opacity values too, but that's not sent to the display. It's pre-multiplied with the red, green, and blue values to give you the final color that you see. Now, in order to provide a smooth user experience, graphical applications like a browser or Illustrator, things like that, and video games need to render 60 frames per second. So however a computer wants to populate the frame buffer, it's going to have to do it very, very quickly. To figure out what color should be assigned to each pixel, the graphics engine needs to project everything being drawn into two-dimensional screen coordinates and evaluate all of the pixels in the frame buffer as either inside or outside of the objects being drawn. And finally, assign a color to all pixels based on the features they fall within, and the programmer's instructions. And this part of the rendering pipeline is called rasterization. Okay, back to triangles. What makes triangles a great fit for these kinds of operations the computer has to execute to make images appear on your screen? And why did the architects of modern computer graphics choose triangles instead of some other shape like quadrilaterals, circles, or arbitrary polygons? Well, from a mathematical standpoint, triangles have a bunch of cool properties that make them particularly convenient to draw. So you probably know that a triangle is a polygon with 3 vertices. It's the most simple polygon there is, and 3 vertices is actually also the minimum number of vertices you need to cover any 2-dimensional area. The interior of a polygon is also extremely well defined mathematically, and they're guaranteed to be convex, which are both properties that make algorithms for determining whether a point is inside or outside of a triangle extremely fast and deterministic. Also, it turns out that all polygons and polyhedrons can be, a polyhedron is a 3-dimensional polygon, like flat-sided shape, can be exactly represented by a finite set of triangles. And similarly, arbitrary surfaces in 3-dimensional space, like this teapot, can be approximated by a triangle mesh. So triangles can help us represent virtually any 2- or 3-dimensional geometry that we want to draw. Computer hardware and computer software could be designed to draw other shapes, but the math for determining whether a point is inside or outside of a triangle is much more quickly calculated and easily optimized than point and polygon algorithms for arbitrary polygons. And choosing one type of geometric primitive ultimately allows every part of the rendering pipeline and software hardware system to be intensively optimized for a single operation, which, as you all probably know, makes things a lot faster and easier. So in computer graphics contexts where speed is not as important, like animated films, which are rendered on massive networks of computers called render farms, where frames take much longer than 16 milliseconds to render, those kinds of use cases often use quad meshes instead of triangle meshes to represent their characters and objects. But even though they're animating the quads in 3-dimensional space, before they get drawn by the GPU, they're still triangulated. So even though they have more flexibility, they don't need as fast performance, they can use quads and deal with those drawbacks. With speed, they ultimately, like GPUs are still designed to draw triangles, so they're triangulated at the last second before they're drawn by the computer. Another property of triangles that is important for rendering is the fact that interpolation between vertices over the surface is well defined. And it's defined by a special coordinate system called barycentric coordinates. Barycentric coordinates are a way to describe any point on triangle's surface as a weighted combination of 3 vertices that linearly interpolates the values of vertices over the triangle's interior. Being able to interpolate in a well-defined way is useful for computer graphics because it allows you to specify vertex-specific attributes, which we denote by A_ there, that can then be interpolated across the surface of the triangle for each interior pixel to determine the final color value. The most common attributes are colors, texture coordinates, which I don't have time to talk about, and normal vectors. So here's a triangle with 3 different colors assigned to the different vertices, and the shading, the resulting shading from interpolating across the surface with barycentric coordinates. Oops. So, sorry. Within the interior of the triangle, the barycentric coordinates always add up to 1. So you can think of like alpha, the alpha coefficient on, vertex 1, beta on vertex 2, gamma on vertex 3. And Interestingly, this is one of the cool geometric properties of triangles. If the intersection point of the three medians of a triangle, which are the lines that intersect with a vertex and the midpoint of the opposite segment, the barycentric coordinates are equal. That's the point, the center of mass if a triangle was a physical object. And so the color at that pixel is, a third of each of the colors summed up all together. And the math involved in describing improving barycentric coordinate system is very cool, but I don't have time, and I'm also not qualified to go into more detail on that. Last triangle property I want to talk about is that all vertices of a triangle are guaranteed to be coplanar. And one of the reasons this is important is because 3D computer graphics uses simulated lighting to enhance rendering and make objects rendered on a two-dimensional screen appear to be three-dimensional. Without light and shadows, three-dimensional objects look flat, like this. How much a surface is illuminated or shadowed depends on its orientation with respect to the light source. The brightness of a point depends on the angle between the light source and the normal vector of the surface, which is the perpendicular vector. Triangles are planar, so the surface tangent is constant for triangles, and the normal vector will be constant over the surface as well. So it's important. And when you render a triangle with a lighting component that is based on the surface normal of the triangle, you get this kind of faceted look, which isn't actually desirable if you're trying to visualize smooth surfaces. But it's still important because if you take that in combination with the ability to interpolate smoothly over the surface of a triangle, you can assign an attribute to each vertex of a triangle as the vertex normal and interpolate that over the surface of the triangle to create an illusion of a smooth surface with your shading code. So to recap, triangles are great, and some reasons why include that they can define or approximate all other shapes and surfaces. They have a well-defined interior, guaranteed to be coplanar. You can linearly interpolate across their surface, and most importantly, they allow you to be able to optimize for a single shape. Why is this not going? Okay. Thank you. And if you'd like to learn more, 3JS is really cool to play around with. Khan Academy has some cool tutorials, and there's lots of resources online for learning computer graphics. It's not that hard. You can do it, and it's really fun. So thank you. Sorry, I went over.